Hello and welcome to my second installment of videos for operations research. Today I'll be going over week 13's assignment about economic order quantity. These two problems should illustrate how to go about finding the economic order quantity Q, and this is the formula we're going to be using for it. So K equals the square root of 2 times K times D over H. Also wrote it twice because my handwriting's not the best. So let's go through this problem and see and focus. Okay. Problem 3.3.1. A consulting firm is trying to determine how to minimize the annual costs associated with purchasing computer paper. Each time an order is placed, an ordering cost of $20 is incurred. The price per box of computer paper depends on Q, the number of boxes ordered. The annual holding cost is 20% of the dollar value of inventory. During each month, the consulting firm uses 80 boxes of computer paper. Determine the optimal order quantity and the number of orders placed each year. So, it's a lot to unpack in that one problem. You can just ignore the mess beneath it. We'll go piece by piece. So, we're looking for Q. And each time an order is placed, $20 is incurred. So, K equals 20 because that is the ordering cost. Now the price per box of computer paper, alright, and the annual holding cost is 20% of the dollar value of inventory. So let's look at the little table here. So this is also a given. So the number of boxes ordered. The price is different for the number of boxes that are ordered. So between 0 and 300 boxes ordered, it's $10 per box. But if you get between 300 and 500 boxes, well, that's $9.80 per box. And if you get over 500 boxes that you order, well, then the price of the box is $9.70. So, with that, we see that annual holding cost is 20% of the dollar value of inventory. So there's going to be three different H's because our H for the 2KD over H, that is going to be each of these multiplied by 0.2. So our three potential H's are 10 times 0.2, which is 2, 980 times 0.2, or 20%, that's 1.96, and 20% of 970 is 1.94. So we're really going to have three different potential economic order quantities that we're dealing with. Now, what is left in the problem to unpack? During each month, the consulting firm uses 80 boxes of computer paper. So each month, that's 80 boxes. So we'll multiply 80 times 12, since there's 12 months in a year. Right there, that's what we're doing. 80 times 12, we get 960. So our K is 20 because of the ordering cost of $20. Our demand, D, is 960 because it's 80 boxes a month times 12 months a year. So that's our K and that's our D, and these are our potential H's. So that's all the things we need for our formula. Q equals square root of 2 times KD over H. So we're going to use that formula 3 times. And I went by price bracket. So least quantity to greatest quantity is how I ordered it. So Q1 would be square root of 2 times 20 times 960 divided by 2. Those two 2's cancel, so it's just going to be 138.56. Now 138.56 is between 0 and 300, so that's a potential candidate for the economic order quantity. All right. And Q2, square root 2 times 20 times 960, but this time the h is different. It's over 1.96, so that's going to equal 139.97. But that 1.96 corresponds to the bracket where the number of boxes is between 300 and 500. 139.97 is less than 300, so we say the minimum value for Q2 is 300. So right now our two potential economic order quantities are 138.56 or 300. And now Q3, square root of 2 times 20 times 960 over 1.94 equals 140.69. And same reason as before, 140 is less than 500. So the minimum economic order quantity for that price range is 500. And then we just basically plug those three potential values in to our total cost equation, which is it's D, so it's like dP plus HQ over 2 plus KD over Q. So we plug those in, and I'm not going to bore you with the algebra. So for Q1, we get total cost of $9,877.13. For 300, we get $9,766. And for 500, we get $9,835.40. So, or $9,835.40. So we have those three potential total costs. That's smaller than that, but this one is smaller than both of them. So we have oh, I see. Okay, so 300 boxes ordered per year is optimal, but we demand 960 boxes per year. So you can only order 300 at a time. So we're dividing 960 by 300. That's 3.2, or 3 orders per year. But I'm gonna be honest with you, it's actually, let's say we're gonna round up, because we've basically got to round up. Yeah, because if 3.2 is more than 3, and you can't round down because then you'd be below demand. So I'm just going to round up and say, it's 3 or 4 orders. You know what, let's not get too nitpicky with it, but personally I think 4 orders per year is optimal because 3.2 is bigger than 3. So yeah, that problem's been completely unpacked, and that is the final answer. Now for problem 2. Each year, Shop-A-Lot Stores sells 10,000 cases of soda. The company is trying to determine how many cases should be ordered each time. It costs $5 to process each order, and the cost of carrying a case of soda in inventory for 1 year is 20% of the purchase price. The soda supplier offer Shop-A-Lot the schedule of... that grammar doesn't seem right. The soda supplier offers Shop-A-Lot the schedule of quantity discounts shown in the table below. Q equals number of cases ordered per year. Each time an order is placed, how many cases of soda should the company order? Alright, storytelling time's over. Time to unpack it. So we have D is 10,000 because each year they sell 10,000. K is 5 because the ordering cost is $5. And we have, let's see, similar table as before. Different ranges this time. Now it's not 300 and 500, it's 200 and 400. I'm mixing things up here. So 20% of the purchase price, that's the same. So 20% of 440 for this bracket is 0.88. 20% of 420 is 0.84 for this middle bracket. And the H for this third bracket is 20% of $4, which is 0.8. So we use the same formula as before, and we're going to have, again, three potential economic order quantities. And so let's see, where did I write that down? Yeah. Q1 is the square root of 2 times 5 times 10,000 divided by 0.88, which is 337.1, which is greater than 200. So before the problem was that the numbers were too small for the bracket. Now the problem is that the numbers are too big for the bracket. So we got Q1 is approximately 337.1, but that's greater than 200. So we're actually just going to say that Q1 is 200. Similar formula for Q2. 2 times 5 times 10,000 divided by 0.84, we get 345.03. Yeah, I'll actually rewrite that again. Yeah, just in case it was worse the first time. Okay. And Q3, I didn't even want to write down the formula. You know it's just going to be square root of 2 times 5 times 10,000 divided by 0.8. That gives you 353, which is below the bracket, so we're just going to say Q3 is 400. The ones that are circled are the ones that I designated to the actual Q. So those are our potentials, and we're going to plug them into the total cost function again. So, where did I plug it in? We're looking at 200. Where did I plug in 200? Q2 works, so we don't need Q1. All right. So I guess we're just comparing Q2 and Q3 because we're trying to order more? Alright, this one's a little sketchy here. Q2 works, so we don't need Q1. Yeah. Where did I come up with that? Sometimes I just have strokes of genius and I just forget where it came from. Q2 works, so we don't need Q1. Well, oh, I see. Okay. Because the price per case is lower as you increase the quantity, you want to actually buy more at a time because the price goes down. And here, it didn't really fit the formula, but for this one it did. So since this is in a higher bracket than this is, that's why Q2 works, so we don't need Q1 because it just won't be as cheap. So we're comparing 345.03 and 400 in the total cost function. So you plug it into that crazy formula and you get 42,289.83. Plug in 400 and you get 40,285. Well, that's a smaller number than that, so that's less cost overall. Therefore, that's the little therefore symbol. Therefore, the company should order 400 cases of soda. Each time an order is placed, how many cases of soda should the company order? The company should order 400 cases of soda. I guess that warrants a QED. Stay groovy, y'all. Stay safe.